From here on out, you're going to want to think of simple harmonic motion two different ways. In our last video, we saw that a mass on a spring vibrating back and forth shows simple harmonic motion. Now, if you place a ball on a turntable and shine a light from a projector, like shown in this picture, the shadow also follows the same motion as the mass on a spring. So circular motion, or uniform circular motion projected onto one dimension, is also simple harmonic motion. And this is going to help us look at our unit circle. In our last video, we said that this position function represented the motion of an object that oscillated if it began at an amplitude of A. Now, when this is not true, when you do not start at an amplitude of A, then we have to introduce a phase constant, measured in radians. Now, this piece down here is the phase. This piece here is the phase constant. Now, these are Greek letter phi's, and this is phi naught. So when you do not start at an amplitude of A, then you need to include that piece in your equation. Now, if you look at the diagram over here, if we were to start at position A, phi naught would have been equal to 0. And that makes sense because it goes back to the original equation that we started with. But let's say that we do have an angle of phi naught. That means, let's say that we're starting at this position here, at an angle of phi naught. Then our new initial position is A cosine of phi. And again, what we're doing is we're looking at this triangle here. This angle is adjacent to, or this side is adjacent to. So our initial position is equal to A cosine of phi naught. So to determine the initial conditions of a situation, you simply set t is equal to 0. So your equation simplifies down to the initial position is equal to A cosine of phi naught. In our last video, we also saw the equation for velocity, which is the first derivative of position. And we said it was negative angular frequency times amplitude times a sine of, now we're adding this additional piece, this omega t plus phi naught. So when I set t is equal to 0, then what we're doing is we're solving for our initial velocity. So the first piece goes away. And all we're left with is negative omega times A times the sine of phi naught. Remember, also in our last video, that we said omega A can be replaced by V max, which is our maximum speed. Now remember that here our position and velocity are both vectors. So if we do get negative values, then it is to the left of our equilibrium position if we're talking about position. And if it's a negative velocity, then we are traveling to the left. Now let's look at a couple of examples. In this first example, what I want to emphasize is solving for our initial position. Now here, our phi naught is equal to pi over 3. So if I put the cosine of pi over 3, I get 1/2. So our initial position is 1/2 A, our maximum amplitude. In the second picture, I'm also starting at 1/2 A, but our phi naught is actually negative pi over 3. So if I do the cosine of negative pi over 3, I still get that 1/2. So my initial position is still 1/2 A. So here we are traveling in a different direction, but again, all this equation tells me is my initial position. And the last picture, my phi naught is equal to pi. So if I were to put pi, cosine of pi into my equation, then I would get -1. So my initial position is negative A. Now if we look at the velocity function, again, what this tells me is the direction that I'm traveling and the speed that I'm traveling at the beginning. So looking at the first picture, if I were to put phi naught of pi over 3 into this equation, I would get the sine of pi over 3, which is a positive number. But I already have a negative there. That means my initial velocity would be negative. And that makes sense because here in our diagram, we do see that we are moving to the left at that point. In our second picture, I have a phi naught of negative pi over 3. So again, if I were to put that into my sine function, I would get a negative value. But I already have a negative there. So then my initial position, or my initial velocity, would have been a positive number. And for my last example, I have a phi naught equal to pi. So if I put that into my equation, sine of pi gives me 0. So my initial velocity, if my phase constant is pi, is 0. In this example, we have an object on a spring oscillates with a period of 0.8 seconds and an amplitude of 10 centimeters. At t is equal to 0 seconds, it is 5 centimeters to the left of the equilibrium and moving to the left. What are its position and direction of motion at t is equal to 2.0? Now, first off, we need a label of our information. We know that the period, which is capital T, is actually 0.8 seconds. The amplitude, A, is 10 centimeters. And we can convert this to 0.1 meters. At t is equal to 0, my initial position, is 5 centimeters to the left. Because it's telling me it's to the left of equilibrium, that says that my phase constant has to be between pi over 2 and pi. This means that it's moving on the top half of our circle, or between negative pi and pi over 2. Negative pi over 2. Either moving at the bottom half of our circle. So again, what I'm referring to, if this is our unit circle, and it's moving, it is to the left of equilibrium, which is here in the middle, it has to be in either of these two shaded areas, which is pi over 2 to pi or pi to negative pi over 2. It has to be one of those two areas because it's to the left of the equilibrium. But now it's telling me that it's also moving to the left. So if it's moving to the left, it has to be on the top part of this circle. That means that we have narrowed it down to just this top section. So my phi naught has to be between pi over 2 and pi. So we can solve for phi naught using our given equation, which was x naught is equal to a cosine of phi naught. Again, this is true when t is equal to 0. I want to solve for phi naught, so we divide by a, and then get the inverse of cosine. To give us phi naught. Again, we know all these values, so I can substitute them in. So this is cosine inverse. X naught, it did tell us again we are to the left of equilibrium, so really I should have put a negative over here. So it's a negative 0.05 meters over 0.1 meters. In this case, it wasn't absolutely necessary to change the units. They would have canceled out either way. And I get 2 pi over 3. And really we should label this as positive 2 pi over 3 and negative 2 pi over 3, because we can achieve this initial position of 0.05 either way. But looking back at the information that we talked about at the beginning, I've already narrowed it down between pi over 2 and pi. So that means that my x value, or my phi naught, has to be positive value. So again, now we have a value for phi naught. Now what this problem is asking for is what are its position and direction of motion at t is equal to 2.0 seconds. Now, all of this is to eventually get an equation for position. So going back to our original function, Once I know the last piece of information, which in this case is omega, once I know omega, I can plug in t is equal to 2 seconds and get my position at 2 seconds. So in order to do that, I need to say that omega is equal to 2 pi over t, which is what we saw in our last video. That omega is 2 pi over 0.8 seconds, which is going to give me a value of 7.85 radians per second. So again, this is my value for omega. So I can rewrite my position function with all of my given information. And now my solved omega. So again, the amplitude was 0.1 meters. Omega is 7.85. I want to go ahead and just put t back in there so we have a general function. And my phi naught is 2 pi over 3. Now I can evaluate this function at t is equal to 2 seconds. So I get 0.1 cosine 7.85 times 2 plus 2 pi over 3. And that's going to give me a position of 5 centimeters, or 0.05 meters. This is 2. Now, because this is a positive value, that means we are to the right of my equilibrium position. Again, because this is a positive value, we are to the right of my equilibrium position. But that just means we can be found at that position. That doesn't necessarily mean we're moving to the left or right. But we also want to know the direction that we're moving in. So for that, we can look at our velocity function. So if we're trying to solve for our velocity at t is equal to 2 seconds, it's not necessary to solve for the initial velocity because we can also substitute. So let's write this out. We know that our equation for velocity is negative omega times a times the sine of omega t plus phi naught. And if we wanted to solve for the initial velocity, then we can use this function instead. But again, it's not absolutely necessary to solve for the initial velocity because we can use it based on the information that we already solved for. So our velocity at t is equal to 2 seconds is negative. Our angular frequency we solved for is 7.85. Our amplitude was 0.1 meters times the sine of 7.85 times 2 for 2 seconds plus our phi naught, which we've already solved for, which is positive 2 pi over 3. When I plug all of that information in, I'm going to get a positive 6.68 meters per second. Again, this is my velocity at time is equal to 2 seconds. Because this is a positive value, this means we are moving to the right. So remember we've talked about energy before in terms of springs. Now the total mechanical energy is still conserved for our simple harmonic motion example of a spring with a constant K, mass m, and on a frictionless surface. So remember that E is equal to kinetic energy plus potential energy, which is 1/2 mv squared, and again the potential energy we're going to have in this situation is 1/2 kx squared. So the particle has all potential energy at x is equal to a. Again, we're not moving at that point, so all of our energy is in the form of potential energy. And the particle has purely kinetic energy at x is equal to 0, again, when we have no stretching or compression. So again, at the turning points, which is at the maximums here, amplitude, the maximum amplitude, and negative a, all of our energy is in the form of potential, so which is 1/2 x k, and then our x is actually the amplitude in this situation. Now, at the middle point, which is our equilibrium, we're going to have entirely kinetic energy, which is 1/2 velocity maximum squared. So we know that in terms of conservation of energy, they should be equal to each other. So what we have at the very bottom, when we get V max by itself, is we have an equation for velocity in terms of amplitude, spring constant, and mass. Again, it is possible for you to see these types of graph on the multiple choice section of the AP exam. So I want you to notice what's happening here. We do have entirely potential energy here. So here we're seeing a energy graph, our potential energy graph curve. So as we approach our equilibrium, we start to decrease in potential energy. At the middle, we have exactly 0 potential energy. As we move away from the middle towards our other maximum, and then our potential energy starts to increase, and that happens back and forth. So you see that this is kind of like a skateboarder on a ramp, just going from one point to the other. Okay, but you do see here that our total energy stays constant all the way through. Total energy does not change. That means my kinetic energy function is going to be this, but flipped. At the middle, we will have maximum kinetic energy. And then at these points, it's going to slow down. Okay, so you have this inverse of this potential energy graph. So here, what I've drawn in pink is our kinetic energy curve. So we know that as we approach our ends, that we start to slow down and then reach our maximum. So at that point, we have no more kinetic energy. And then we can come back towards the center and reach our maximum kinetic energy here in the middle.